So what that means for me is, if I've got 1/8" plate, or 1/8" sheet, pardon me, how many thousandths is that? Well, it's 0.125 inches. So I got 125 thousandths. What that means is my starting amperage is going to be about 125 amps. So 16 gauge. In inches, it's 625-ish. 0.0625. So 62.5 thousandths. So that's going to be approximately 62 amps. This works really well up to about 10 gauge, up to about 1/8" plate. After that, it doesn't work, because according to this, if I was going to weld a quarter, well, how much is a quarter? It's 250 thou. So does that mean I set my welder for 250 amps? Usually no, I'm not going to do that. With steel and stainless steel, you almost never need more than about 160, 170 amps to weld anything. If you're in tight, you can get the heat in quick, you can run with it, you don't need to run 250 amps. Your tungsten's not going to last very long, 250 amps, I guarantee you that. So, quarter, I'm 160, 170. And I just get really close, give her a bunch of heat, and run with it. But for most sheet metal we do, this is going to work really well. Works same thing with aluminum. I usually just go up from that roll with aluminum, because aluminum is such a great conductor of heat. It pulls heat out very quickly. So if I'm welding 10 gauge aluminum or 1/8" aluminum, instead of 125, I might be 145. I just want more heat, and it'll make things work better. Aluminum especially, I talked about it before, number one problem people have is being either too far away or not hot enough. Aluminum especially, hotter is better. Biggest problem people have with aluminum is just not welding hot enough. If I'm welding 1/4" aluminum, I'm going to have that thing set on kill. I'm going to be 250, 300 amps. So I can get into it, get it hot quick, and get out of it. So anyway, for us, 1/8" plate, which is what we're going to weld on, about 125 amps. The other plate we're going to weld a lot of, we'll do 1/8", we'll do 16 gauge, we'll do 14 gauge, which is 0.74? 0.074. I think that again if you read it, 0.074-ish. So about 75 amps, somewhere in that range. So those are my guidelines for like flat. If I go out of position, and out of position is either going to be vertical or overhead, I'm going to go down about 10%. Okay, so at this, at 125 amps, if I go down 10%, that's 12.5 amps. If I'm doing vertical, I'll turn this down to 110-ish, see what happens. As you get more comfortable with TIG, you'll start doing that less and less. You'll stop, you won't turn it down as much. You'll just learn how to deal with it and run with it. Stainless steel. So stainless steel, the additives in stainless steel, chromium, stuff like that, the nickel, they make it a poorer conductor of heat than mild steel. So what that means is it doesn't pull heat out and draw heat away from the weld zone as quickly as other materials we used to do. So we can go down in heat on that as well, because the heat stays more localized for longer. That's also the reason stainless steel warps so bad, is it stays hot locally for so much longer after we weld it. So with stainless, that 10% guideline that I'm going to go down for out of position welding, I'll apply that to stainless steel as well. I'll probably just go down 10% when I'm welding stainless. If I need to go back up, I can, but it'll give me a good starting reference. The other big thing when we're talking about aluminum versus steel and stainless steel, or really ferrous versus non-ferrous, steel and stainless steel being ferrous, aluminum being the big one we weld as non-ferrous, is the current we use. Let me back up a little bit. So there's 3 kinds of currents we can have. We talked about this in our stick unit that you weren't privy to because that was a while ago. So there's 3 kinds of current we can have. We can have AC, we can have DC negative, or reverse polarity, and we can have DC positive, DC electropositive. AC is aluminum. That's what we use for aluminum. DC negative we use for steel and stainless steel. DC positive we don't use for TIG welding, generally. So the differences between these are, key difference is how much heat they put on to each half of the equation. And the equation is heat on base metal versus heat on tungsten. So aluminum, or AC, pardon me, is a sine wave. It is the 60 cycle, well, from the wall, it's the 60 cycle sinusoidal wave you see. It's this number. Everybody seen that? AC is 50-50. 50% and 50%. 50% heat on base metal, 50% heat on the tungsten. AC, we use AC for aluminum because half of this cycle, this up here is DC positive, this down here is DC negative. This DC positive is actually, I've got my tungsten down here and I got my plate. DC negative is actually sending electrons that way. DC positive is actually sending electrons that way. And this DC positive half of this AC waveform is lifting the oxide off the aluminum, allowing us to weld it. Aluminum's got a skin on it that melts at 3,000 degrees. It's an oxide, aluminum oxide. The aluminum melts at 1,300. So the aluminum will melt before the skin, that skin, that oxide layer on top, ever melts off. It doesn't work. So that DC positive side of that waveform blows that scale away, that layer away, so we can weld it. When you look at an AC aluminum weld, you'll see a kind of a frosty white line running down both sides of the weld. That's actually the cleaned area from the cleaning action of that DC positive. So AC 50-50. DC negative is basically 66 and 33. 66% of the heat on the base metal, 33% on the tungsten. We use this for steel and stainless steel because it saves our tungsten. It gives us more heat on the base metal so we can weld faster, and it's got less heat on the tungsten so the tungsten doesn't melt. Now, the melting temperature of tungsten is under the temperature of the electric arc, but how we get away from that is we're not putting all the heat on it at one point. We're only getting a third of that arc heat on the tungsten when we're running steel and stainless steel. Now DC positive, the reason we don't use for TIG welding is this is the opposite. It's 33 and 66. So 33% on the base metal, 66 on the tungsten. If I can spell. So in the old days when I started welding, we would use DC positive to ball the end of a tungsten we're using to weld aluminum, because in those days they wanted a nice round end of the tungsten. So you turn your machine on DC positive, hold it off the table a little bit, feed it the amperage, and it would instantly just melt that tungsten back into a nice round ball because there's so much heat. With the inverter machines, you don't have to do it anymore. It almost never gets used, but that's the purpose of it. So for us, it's going to be AC and it's going to be DC straight, or DC welding. Everything's got three names. DC straight, DC negative, DC yeah. So let's see. How clean is clean? Can't ever be clean enough TIG welding. Never be clean enough TIG welding. A lot of stuff, they don't have to be that great. Your coupons, if you hit them with a sander real quick, they're fine. But for stuff I really want to turn out nice, I'm going to wipe everything down with some kind of degreaser, a lot of times acetone, to get any trace of oil off of it. It makes a difference. Can't ever be too clean. If you've got a pair of gloves that you've been changing oil in, don't use those for TIG welding. You're going to transfer that oil to your filler metal. You're going to transfer it to the tungsten when you're inserting it into the torch. You're going to transfer it to the plate while you're carrying it around. Don't do that. Everything needs to be clean when you're TIG welding. That's about it. What's due this week? Form assignment. I'll watch all the videos. The end of chapter test. That's really about it. If you have any questions, reach us online. Come talk to the lab. We'll answer them best we can. Thanks.